Welcome to module 28 of database management systems. We have been discussing about indexing and hashing. This is the third module in that continuation. In the last module, we have taken a quick look at the balanced BST and specifically a different kind of inline data structure called 2, 3, 4 tree, which can be of very good use in terms of understanding B plus tree, which we want to study in this module, and we will also take a quick look at the B tree. So, now B plus tree is the main data structure one of the main data structures to be used for index files. So, B plus tree has now what we have seen the ordered indexes, we have seen the index sequential files where you could keep the index file in a sorted manner. In the primary index you could build secondary index on that and so on, but that is not an efficient way of doing things, because the performance keeps on degrading as the file grows, since many overflow blocks will get created, because certainly if you are growing, then naturally you have created say sparse index on certain values, and if there are more records in that bucket, then naturally you need to have linked buckets. So, periodic reorganization of the entire file becomes required, which is a very costly affair. In contrast, the advantage of B plus tree is it automatically reorganizes itself in small bits and pieces with local changes and so on, whenever insertions and deletions happen, and the reorganization of the entire file is not required for the purpose of maintenance. Of course, there are a little bit of disadvantage. The extra insertion and deletion overhead exists for the small micro reorganization. There is a little bit of space overhead, but in the face of the advantage that we get, it outweighs the advantages, outweighs the disadvantages, and B plus trees are used quite extensively. So, just recall the notion of 2, 3, 4 tree that we had discussed, and look at this diagram. So, 2, 3, 4 tree have different types of node, 2 node, 3 node and 4 node. So, we said that there could be a node which can be only partially filled, and it has a different number of children pointing to the conditions of how different keys are ordered in that particular node. So, here I show an instance of a B plus tree, which is basically trying to represent this file in terms of the creating indexes. So, if the index is actually based on the name. So, this is the root node that you have, and for an instance we are taking a structure where every node can have 3 data items and 4 links, and it could be more, it could be less, but this is just for an example. So, as you can see, so if we have this link on the left of Mozart, then it means all keys which are less than Mozart will be available on this link below. The link that exists here is for all keys which are greater than Mozart and less than, right now there is nothing. So, those will occur here. So, as you can see that Einstein, Gold, Brand, all these will come on this link. Srinivasan, Singh, Wu, all these come on this side. The Mozart itself comes on this side. Now, if I look at this node, the next level node, now this link has values which are less than Einstein, as you can see. This has values which are between Einstein and Gold. So, Einstein and LZ, these are values which are more than Gold. So, this is and as you can see that though all nodes are shown to be of the same type, as we had mentioned at the end of the 2, 3, 4 tree discussion, but it has variable number of entries. So, the number of links are between n by 2 and n. So, n here is 4. So, you have at least 2 entries or maximum up to 4 entries that can go on here. So, So, this is the basic definition of a B plus tree. All paths from root to leaf are of the same length. This is again something you should observe here, because if you see all of these paths, all of them have the same length here, then the length is 2. So, that is a basic property of 2, 3, 4 tree generalized into B plus tree. So, each node that is not a root is a leaf level, has between n by 2 to n children. Leaf node has n minus 1 by 2 to n minus 1 values, and if the root is not a leaf, then it has at least 2 children, and if the root is a leaf, there is no other nodes in the tree, then it can have between 0 to n minus 1 values, which are quite obvious. So, naturally a typical node will look like this, where the pointers and key values alternate, starting with a pointer p 1, then key k 1 and so on, and ending with the pointer p n. And the search keys are strictly ordered, k 1 less than k 2 less than k n minus 1. These are facts that we have seen for 2, 3, 4 tree. So, for a leaf node, the pointer p I points to the file record with the search key k I, and if there are two leaf nodes L I and L j, and I is less than j, then L I's search key values are less than or equal to the L j's search key values. So, this is the basic ordering that we had seen in 2, 3, 4 tree, that is what is getting generalized. For a non-leaf node, similarly, all search keys in the subtree which p 1 points to are less than k 1, then for all that p n points to are greater than k n minus 1, and in the other cases they are between the two consecutive key values that exist between the pointers. So, this is an example of a simple case which is n, where n is equal to 6. So, since the internode connections are done by pointers, logically closed blocks are not physically closed. So, that is a key idea, that is a key observation about the B plus tree. So, two nodes, the records which are logically closed may not actually be physically closed, because the pointers actually define the closeness in terms of the ordering of the values. So, B plus tree contains relatively small number of levels. We will see what that level would be. So, what will happen if the level below root has two values at the most, at least, and the below that will have n by 2 values, because every node has to be at least half filled. We have said every node will have to have n by 2 links to n links, it cannot be less than that, less than n by 2 links. So, the next level has n by 2, then the next level has 2 into n by 2 into n by 2, and so on. So, every time every level you go down, you can basically increasing by a factor of n by 2, which as you all know simply means that the number of levels or the height is log k to the base n by 2, where k is the number of search key values that exist on the tree. So, larger the n, smaller is this value. So, larger the node size is smaller is the height, and therefore, the number of insertion number of access operations that need to be performed. So, insertion deletions to the main file can be handled efficiently, as the index can be restructured in logarithmic time, as we have just seen. So, search should be very simple, because it is just an extension of what you did in 2, 3, 4 trees. The algorithm is given here. I will skip it, because we have already done this in detail. Now, what we introduced, I started saying that there are no duplicates. So, the keys follow strict ordering, but the whole assumption will also hold good if you allow the equality between the consecutive keys, but only difference is there could be multiple keys which are all equal, and if that happens, then you have to use the same key value present at the two leaf nodes, and the parent will also have the same leaf node, same value. So, for doing in the case of such duplicates, we will have to little bit modify the procedure for doing the search and say printing all values and so on. So, you could go through that. So, if there is a k search key values in the file, then let us see what the cost is coming to actually. Then the height of the tree is not more than log k to the base n by 2. So, if we say that the every node, so how large would be the node? Now, again I would remind you that we are moving from 2, 3, 4 tree, which was a in memory data structure, to a external data structure. So, our main cost is the disk access. So, what would you like to make this node size? If we make the node size too small, then there will be too many nodes and every node will have to be accessed. So, as you can see, that is log to the base n by 2. So, we benefit by making n larger. Larger the n, this log value or the height will be less. But can I make n arbitrarily large? Then n will not fit into one disk block. So, it cannot be accessed in one fetch from the disk to the memory. So, we would typically like to make it is customary to make the node as the same size as the disk block, which is typically say 4 kilobyte or 8 kilobyte like that. And therefore, if that is a size, then the n will be typically around 100, because if 4 kilobytes is a total space, and if I assume that 40 bytes per index entry, which is very typical, then n would be about 100. So, if I assume that my index file has actually 1,000,000 search key values to look for, then I will need 1,000,000 to the base 100 by 250. So, 1,000,000 log 1,000,000 to the base 50, which is approximately 4 node accesses in a lookup table. So, that is amazingly fast. If you contrast this with balanced binary tree, which will be log 1,000,000 to the base 2. So, which would be about 20 node accesses, 20 disk accesses for this lookup. So, this is the core reason that B plus trees are preferred, and with this even when you have couple of million records in a table, you can actually manage with a very small number of node accesses for the lookup, which makes the realization of all algorithms possible. In the next couple of slides, I have discussed about how to update B plus trees, talked about the insertion and the deletion process. I will skip them in the presentation now, because as we have discussed the process of insertion in depth in terms of the 2, 3, 4 tree, the only difference here is that this is in a generalized framework, but follows exactly the same idea of node splitting, and keeping in mind that in case of 2, 3, 4 tree, you move from 2 to 3 and 3 to 4 node here. All that you will have to remember is you always make sure that you have every node half filled, because n by 2 is the minimum requirement. So, you keep on inserting in a node till it becomes full. When it becomes full, you cannot insert any more, you divide it into split it into 2 nodes, so that each one of them become at least half filled, and that is a simple logic, and rest of it you can figure out by following on the 2, 3, 4 tree insertion. So, this is the first algorithm. Then we have shown here the strategy to splitting the node, which I have just discussed, and the same notion of propagating the middle element of the split continues here. Go to next, and here the examples shown in terms of the B plus tree before and after insertion of a certain key. You can go through that and convince yourself there are some more steps in the algorithm. Please go through them carefully and try to understand the whole process, and then this is the basic algorithm written in a very cryptic pseudocode, I should say. You should refer to the book actually and study the whole pseudocode to understand the algorithm better, and work through examples as well. Similarly, there are examples of deletion in B plus tree. So, the trees are shown before and after deletion of Srinivasan. Then if you delete like that, now in case of in contrast to splitting, now you will have merging of nodes which will start happening. There are some more steps in the deletion shown here. Please go through them and work this out. This should not be, you should not have any difficulty in understanding them given your background in the 2, 3, 4 tree. So, more steps in the deletion. So, this is the deletion process in terms of algorithmic steps and what you need to do for deletion. So, this is all detailed here. So, B plus tree file organization is takes care of the degradation problem in terms of the index files, which would have happened if we had used pure ordered indices like the index sequential access method for storing the index files. So, that is now taken care of, and even the data file degradation problem can also be solved by using B plus tree organization. So, it can be used for both maintaining the index as well as the actual data file, and the leaf nodes in the B plus tree file organization store the records instead of pointers. So, you finally have the records there, and the leaf nodes are still required to be half full since the records, but since records are larger, then the maximum number of records that can be stored would be less than the number of pointers in a non-leaf node. Insertion and deletions are handled in the same way as in the B plus tree index file. So, here all that we are explaining, that so far we have explained the whole B plus tree in terms of index file organization, and we are saying that you can do the same thing with the data file, and only at the leaf level you will have to actually keep the data records for maintenance. So, this is showing some instances of the B plus tree organization. So, there are a couple of other issues, the record relocation and secondary index. If a record moves, all secondary indices that store record pointers will also have to be updated. Node splits in B plus tree file organization is very expensive. So, what we do is we use primary index search key instead of record pointer in the secondary index. So, in the secondary index we do not actually keep the direct record pointer, instead we keep the search key of the primary index, and you know that the primary index can be very efficiently searched. So, what happens is when in the secondary index, when you have been able to actually find that you do not get a pointer directly to the record, but you get the search key through which you can use the primary index and actually go to that. But with that you get rid of the requirement of maintaining different secondary index structures and getting into several record relocation problems. There are your indexing also may need to take care of the issues of string. Your variable length string could be keys which have variable fan out, and so the general strategy in handling indexing with string is to do a kind of what is known as prefix compression. So, you kind of find out what is the shortest prefix which can distinguish between the strings. So, if you have Silas and Silbert's, then you can easily make out that SILB would be a separating string between these two. So, SILB will match with Silbert's, but not will match with the first one. So, you do not need to look beyond that. So, we can just keep enough characters to distinguish entries in the subtree separated by the key values, and keys in the leaf node can be compressed by sharing common prefixes. So, that is a very common strategy. Next, let us just take a quick look into the B tree index file, which is another alternate possibility. The basic difference between a B plus tree and B tree is B tree allows search key values to appear only once. If you remember, in the B plus tree your search key values which occurs in an internal node keeps on occurring at multiple node levels also. B plus B tree does not allow that. The search key in non-leaf nodes appear nowhere else in the B tree. So, if it does not, then naturally the question is where will the actual record value be found out for this key. So, what you do is in the node itself you introduce another field along with the key, which is the pointer to the actual record. So, as you can see here, let us get back. So, as you can see, this was the general structure of the B plus tree node, And now what we are doing is we are putting in separate pointers along with the key, which will actually maintain the data for that key, which will be pointers to the actual record, because this earlier in B plus tree all records finally appear in terms of the leaf level nodes only. Their pointers come in the leaf level, whereas here there is no repetition of the search key along the structure. So, they come wherever there. So, let me just show you an example. So, if you look into this carefully. So, this is what you have seen is a B plus tree. So, you can see that Mozart happened here, it also happened here, and this is the leaf level. So, from here actually you get pointers to the record for Mozart. Similarly, Einstein happens here and it happens here. Srinivasan happens here, and so there are multiple times they are happening. This in contrast is a B tree representation, where Einstein, if it happens, then alongside with it the pointer to the Einstein's record exists. If Brand's happen here, along with it the Brand's record exists, and Einstein would not happen anywhere else in the tree. So, you do not have this second instance of the Einstein or this instance of the Mozart in the B tree. So, naturally that is the basic optimization that B tree does. So, it has advantages. It may use less nodes than the corresponding B plus tree. Sometimes it is possible to find the search key value even before reaching the leaf node. So, search could be efficient, but it does have a lot of disadvantages, because what happens is only small fraction of all search key values are actually found early. Non-leaf nodes are larger now, because you have pointers to the data as well. So, the fan out gets reduced, which means that the number of children you can have gets reduced. So, though you are expecting to get a benefit because you are not having to go to the leaf every time, but you pay off because your fan out gets less. So, if your fan out gets less, naturally the tree has a greater depth now, because you are fanning out less number of children at every node. So, it has a greater depth. So, eventually your cost increases. Naturally the deletion insertions are more complicated than in B plus tree, and implementation is more difficult. So, typically the advantages of B tree do not outweigh the disadvantages. So, it is not very frequent that you will use B trees, but they are used at times, but that is not a very common thing, and we stick to B plus tree for both of the data file as well as index file storage. So, in this module we have understood the design of B plus tree index files in depth for the purpose of database persistent store, and I would again remind you that whole discussion of how B plus tree is organized and how operations of access, insert, delete are done in B plus tree, I have introduced them in keeping in parallel with the simpler in-memory data structure for this, which is the 2, 3, 4 tree discussed in the last module. So, while going through the insertion deletion processes of B plus tree, if you have difficulty following, I would request that you go back to the 2, 3, 4 tree. That is kind of the simplest situation that can occur, and understand that, and then you come back to the specific points in the B plus tree algorithm. And also always keep in mind, while you refer to 2, 3, 4 tree for understanding, also always keep in mind that in case of B plus tree all node types are same, and the basic requirement is every node must be at least half full all the time, except of course for the root. And in addition, we have also familiarized with B tree, and reason that B tree possibly is not a very powerful, is not powerful enough, it does not give enough advantages, so that we would like to use it in place of B plus tree.